It's a pleasure, and welcome everyone to the third lecture in this lecture series on sharp restriction theory. So the first two lectures were about sharp Euclidean restriction theory. We talked about spheres as prototypes for Stein-Thomas, and then we took a bit more of a PDE approach and went from Stein-Thomas to streetcars. Streetcars Schrödinger and wave, which means restriction on parabolas and curves. Today we'll do discrete analogs. Okay, so we'll be focusing on finite fields. And so let me start with the introduction. The full analog analysis on finite fields. So F will be a finite field. Sometimes I will write F cube with the side effect that it has Q elements. This is a finite field with Q elements. Q is necessarily a power of a prime. And in this talk, our primes will be point. Okay. So what P equals 2 is also a prime, but for what I'm going to say today, it's simpler with good potential to okay, once we have a finite field, we can take a d-dimensional vector space over the finite field. And in some sense, FB is similar to R. What do I mean by this? Well, it's similar in a number of ways. Both have vector space structures, both have a variety of directions. In particular, it makes sense to define the case sets, both in RB and FB. Then there's some elementary geometric properties that are similar. For instance, two distinct lines in FB intersect at mostly one point, and through two distinct points in FB, they belong to exactly one line. Right? This happens in FB the same way as it happens in RB. At the same time, FB is also not similar to RB. There are important distinctions. For instance, in FB, there's no distinction between small and large angles. There's no scaling, and some aspects of the geometry in FB are rather exotic, as I hope to illustrate later. Okay. All right. So in the late 90s, Tom Wolf, I guess it appears in the 1999 paper, proposed the Decay set injection in FB. And I guess once you have the Decay set injection, you also talk about the Decay maximal function injection. So I learned last week that these were proposed by Jim in a lecture series in the 90s at the University of New South Wales. I'm not mistaken.
No, but not in the finite field case.
Not in the finite field case.
So
It's
this
with
is both. This is both.
Okay, then this is correct. Yes.
Yeah.
I guess there were other discrete
I knew
analogs.
about this. Yeah, yeah.
Okay,
There are others.
thanks. So in finite fields, these two problems were famously solved. The first one by here in 2009, and the second one by Oliveira. One year later, and of course, the big breakthrough was to realize that the polynomial method was the right to approach. And since I briefly talked about other discrete analogs, let me just mention some more recent work. Okay. Discrete analogs. They show up in a paper of Jonathan and Jim. Show up in 2018. This is written version of the suggestion to explore the restriction decay problem over rings, C1 and Z, and also over the p-adics. Then some of these problems, the decay version of these problems had some solutions, partial and with solutions. For instance, Oliveira in 2020 established a decay set conjecture over Z mod NZ when n is square free. That was the first particular case they considered. Then Arzovsky in 2024. Again, these dates are not chronologically ordered just because these are publication dates, but this is more or less order in which they showed up on our head. So as of the proof beyond the conjecture, and then Qatar, I guess, is a follow-up to his work here in 2024. Established a set conjecture on Z not NZ for general N, not just N which are square field. And finally, Salvatore in 2022, published version, established the Cahill conjecture over so-called local fields of positive characters. And so these are all pretty recent results and show that these discrete analogs of harmonic analysis are hot topic right now. Okay, so I don't want to talk about the Cahill, I want to talk about restriction. So let's do restriction theory on FE. Okay. And of course, we know that restriction is equal to extension, and especially in the finite field setting, is sometimes more useful for what I want to say in the context of sharp restriction to talk about the extension column. Okay, so we start with the function f, which is defined on some set of frequencies. So this is a subset of FB star, and star is here just to denote the dual vector space. And as vector spaces, they are isomorphic, FB and FB star, it's just that they come endowed with different measures. The natural measures are different. So this comes endowed with counting measure, you just count the number of points, remember that everything is finite here, right? You can just count. And here on FB star, you endow it with a normalized counting measure, so that the total measure of FB star is also. Okay, so we take a complex valued function that takes values on this set of frequency sigma, which we call, for the lack of a better name, surface. And it's important that this comes equipped with normalized counting measure as a subset of FB star, whereas FB comes equipped with the usual counting measure. Okay? All right, so once we have a function like this, it's just like having a complex valued function on the sphere in lecture 1. We can define its extension. So f sigma hat at a point x. I'll try to be careful whenever I have vectors on fb or fb star. I'll underscore them to recall that they are vectors. Okay. So f is a function on sigma. Sigma is a subset of the dual vector space P, so we should consider the normalized counting measure. So we divide by the number of points, and we take a sample of C sigma. F is C B X dot C. Okay, so this dot represents the usual inner product of FD or FD star. They're isomorphic, and E of X is the exponential of 2 pi I times the trace of X divided by. Okay. So here there's P and there's N. Recall that we are working on F Q, and Q is Q here. Okay. So this P is the prime number, this N is the exponent. All right, so what's this trace map? This trace map, PRN, is a linear map from FQ to FB. So you see, if you want FQ as a vector space over FB, and when X in FQ, you associate the sum of always X plus X to the P all the way up to X to the P to the N minus. So when N is 1, that's when your base field is. Do you have a question?
Yeah. What is sigma here on the left hand side? If sigma.
Sigma.
Yeah.
That's the normalized counting measure on the surface.
Oh.
So I should have given it a name.
And what is the effect on the right hand side? Like there is no sigma on the right hand side. Right?
Well, since it's normalized counting measure, you see because you're just counting points divided by the total number of points on sigma.
Okay.
Okay. Thanks. Any good questions? No? Okay, so this is the trace map. Notice that when N is 1, that means your base field is just FP. This is the identity map. For higher N, it turns out that this map is linear. Of course, this does not look like a linear expression, but it's just well, x equals x to the p on FP. More importantly than it being a linear map, it can be used to classify all linear maps, all FP linear maps from FQ to FP. Right, so a complete list of those maps can be given in terms of the trace. Okay, so of course there's some orthogonality here. Let me emphasize that so we will use it. So the orthogonality coming from this map, the most basic expression is that if you sum Ex over all x in the base field of x cubed with x0, which means that there's a vectorial version of the same thing. If you do it with x dot c, where now x and c are vectors in FP, not just elements in Q. Usually you will get 0, unless c is 0, at which point you get the number of elements q to the b. Okay, so you know, q to the b if c is 0, it's space, and 0 elements. Okay. All right, so let's write our first restriction inequality, the extension inequality in this case. So FC. We want to try and bound it on LS. This is LS of FB, which, as I said, comes equipped with a counting measure. We're going to call it EX. This is bounded by some constant. Let's call it a constant R star to denote this extension. It's the extension constant associated with the surface sigma, and this is an LR to LS estimate. Usually I would write LP to LQ, but P and Q are taken, and P is the prime, Q is the power. And this is F, LR, sigma BC. Okay, so that's our extension inequality. And the question is for which exponents R in S do we have a bound on this constant? By the way, we can save time and decide this is the best constant. Right? We'll be interested in best constant, so that's the best constant for which this inequality holds true uniformly in R and S with a bound that's independent of the field. Okay, that's the important. See, R S, I know this constant should be independent of the constant. Because if you allowed for dependent constants, the inequality would always be true. But these are finite numbers. There's a finite number of points, so we have to be careful to formulate the restriction probability. So the point is the bounds have to be independent. In that case, we say that extension holds. R sigma star R to S equals. Okay, so what are examples of interesting surfaces which have been considered in the literature? So examples of sigma. There's a parabola. It's just a set of points. C tau, C is a vector, in F is star. Tau is a scalar, in star. I'm still trying to make an effort to keep the stars neatly where they belong. That will probably drop that at some point. And this is just tau equals c squared. And here c squared is just an abbreviation for the inner product of the facility itself. C is a vector, right? It's T. So there's an inner product, and whenever you dot a vector with itself, I'm just calling that as c squared. Okay, so this is of course finite field analog of the paraboloid that we considered on lecture 2 related to Streetmaster Schrödinger. Then there's the cone, gamma B, which is the set of points C, tau, and sigma. So C is a vector, tau and sigma are scalars. So I'm giving them the F squared. Such that tau sigma equals c squared. And for some technical reasons, which I will explain in a bit, I'm excluding the origin from the code. Okay. So this is of course the finite field analog of what we call the one code, the one shifting code, in Euclidean space. And I would also like to introduce a new surface that we have not considered before, which is the saddle surface or the hyperbolic parabola. Right? Of course, sharp restriction theory of Euclidean setting makes sense for the hyperbolic parabola, but pretty much nothing is more. That's why I haven't talked about it. But I will. So this is the second points C and tau, both C and beta vectors. And tau is a C. Okay, this is tau equals C of beta. And as I said, this is the final analog of the saddle surface or hyperbolic parabola. Okay. All right, so this version of the extension problem was first considered by Mock and Hopper. They have a nice 2004 paper in which they proved that R sigma star from L2 to L4, so they consider L2 to L4 extension inequalities, and they show that this holds in the sense that I explained before, so with constants that are independent of the base field, so that makes sense. In three cases, if sigma is the one-dimensional parabola, the two-dimensional parabola, and the two-dimensional. Okay? They have other results, but these are the ones that are more relevant for what I'm going to say today. This was an influential paper, so many people followed. I have here just some names: Jozovich, Ho, Lee, Luko, Fan, Yudnev, Shredel, Young. There's vast literature of people trying to advance the knowledge of the restriction problem for the general surfaces, the variety of surfaces in finite fields. Contrary to the KK problem, the restriction problem on finite fields is open. Okay, there's progress, there's pretty spectacular progress in some cases, but the general problem is just one example that makes the association between FD and RD a bit closer is a relatively recent result by Mark Luko in 2009. This Jan's paper, in which he proves that restriction implies KKL also in FD. Okay, this was not known. The connection between restriction and KKL is well established, pretty well studied in the Euclidean setting. In finite fields, it took almost 15 years since people started investigating the problem to realize that restriction was KKL. All right, so let's make this short. I have some slides, also because I would like to recall, so these are slides from the previous lectures, we've seen them already. But I would like to briefly recall the elements of sharp Euclidean restriction theory that are important, that we've seen in lecture 2, and that are important to make the comparison, the bridge to finite fields. Okay, so the next 2 slides are just revision. All right, so on Tuesday, we basically talked about sharp restriction on parabola. So we're in the Euclidean setting now, back to RD, and we talked about the parabola and the curve. So the parabola is related to the Schrödinger equation. There's an L2 to L2 plus for the Strickers inequality, which was an extension for the parabola, the extension on the parabola. This exponent 2 plus 4 over d turns out to be an even integer in all dimensions when d is 1 and d is 2. And so people attack the problem and try to make it sharp. I mentioned all these works, Osawa Tsutsumi for dimension 2, Hundertmark Jarvinsky, and more or less in parallel Fossey for both pure normal cases, BPCH with an alternative heat flow approach, Gonsalves with orthogonal polynomials. They all prove that the Gaussians are the unique maximizers of inequality 1 in all dimensions. There's a conjecture by Lieb that this should hold in all d greater than equal to 1. But this is open in dimensions greater than equal to 3. And Chris Gilligan had this result that told us, wait, don't get too excited. If you don't do L2, if instead of L2 you consider LP to LQ extension from the parabola, Gaussians will never have a chance of being global maximizers unless P is. They won't have a chance because they are not even critical terms. Right? All right, so I talked about all of this. What I didn't tell you is a version of Chris kilogram for the hyperbolic parabola. Okay, so for the saddle surface, we didn't talk about it on Tuesday. So there was also an implicit conjecture that Gaussians could sometimes be global maximizers there. And Lucas Oliveira and Dr. Souza wrote a short paper just excluding that possibility. So that's the title of the paper. Gaussians never externalize Strickers inequalities for hyperbolic parabolics. And that's pretty much because they fail to be critical points for all exponents, including p equals 2. Okay? And by the way, the existence of maximizers for Strickers, hyperbolic Strickers is known. So the nature of the maximizers remains quite mysterious. The obvious candidates don't have a chance. All right, so this was parabolas. What about cones? So cones are associated to the wave equation. We've seen that. There's the h1 half, the L2 times d plus 1 over d minus 1 Strickers inequality for the wave equation. This exponent is precisely the same as the Stein-Thomas in one dimension lower. That corresponds to the extension of the two-sheeted cone. This Strickers inequality has been put in sharp form by Foster, but only in dimension 3. It shows that if you take this, what we call the conformal factor as f and 0 as g, that's a maximizing pair for the inequality, and all other maximizing pairs, you get them by letting the wave propagator act on this function and applying the Poincare group of symmetries. That's what we see. Okay, he conjectured that this should be the case for all b greater than or equal to 2, but that's not true when b is even. If we want to have a list of all maximizers, we noticed that it was easier to go to the Fourier side, because then the Fosskians are just this function exponential minus c divided by c when you let the group of symmetries play. And that's what we find in terms of the parameters A and this. All right, so I also talked about the usefulness of the Penrose transform to establish a wave version of the Chris kilotron whisper. Right? That Fosskians only have a chance to be global maximizers if and only if p equals 2, because otherwise they're not able to do it. Again, maximizers exist, but if p is not 2, we don't know what they are. All right, so that's the 3-minute version of lecture 2. Now, what about doing the same thing in the discrete world, for instance, with finite fields? Not much was known. Actually, I think nothing was known in terms of sharp inequalities, essential inequalities in finite fields. We have some recent results. This is joint work with Christian Gonzalez Riquelme. He's a postdoc in Técnico in this. Okay. So I have 6 results. I'm going to present them to you. They're in slides because it will take a bit of time to write them down. And then we'll focus on the proof of theorem 1. Okay. So theorem 1 is a sharp version of this L2 to L4 extension on the 2-dimensional parabola in F3. Okay, so you have the L2 to L4 extension in both. Comes with a constant 1 plus 1 over q minus 1 over q squared. This constant is best person, and this inequality is an equality when f is a constant function, or more generally when it has constant values. Okay. So of course, notice that this constant is uniformly bounded by 1, so definitely that's what we're in the spirit of what we expected, it's independent of f. As q goes to infinity, the constant tends to 1. But this is still not completely satisfactory because, I mean, I'm giving you one example of a maximizer, but I'm not telling you the complete family of maximizers. Okay, so that's the content of theorem 2, which requires an additional arithmetic assumption on q. Okay, so q here has to be common to 1 mod 4. That means that -1 is a square in FQ. And that makes the analysis possible. And our result says that for this inequality 2, f is a maximizer, basically if and only if it is a Gaussian. Of course, what does Gaussian mean in finite fields? Well, this is a possible interpretation of the Gaussian. So it's formulated in terms of the trace, but if you don't want to think about the trace, right, there, just think about the case n equals 1, then the base field is fp. And so that's just the exponential of the constant times linear part in eta, linear part in zeta, and then the quadratic part that makes it Okay. Yeah, so this is so notice that the reason why I'm assuming Q to be equivalent to 114 is that -1 is the square, so I have this square root of -1, and then I can take two lines, the line direction 1 omega and the line direction 1 minus omega. And that just turns out to be the convenient way to parameterize this space of fields. Okay. All right, so both of these are on the paraboloid. What about the parabola? So the one-dimensional parabola. For that, there's an L2 to L6 extension inequality. We also put that in sharp form. Equality holds for constant functions and more generally for functions with constant modulus. An interesting twist is that this proof only works when b is strictly larger than 3, because at some point we're reducing this to a convolution of a threefold convolution, and the threefold convolution sort of degenerates into something intractable when these. All right, so these were parabolas and parabolas. What about the saddles? So the hyperbolic parabola, for which in the Euclidean setting, pretty much nothing is known, just know that the Gaussians fail. So here, interestingly, that's where we have the most complete and satisfying result. So for all Q, independent of converse classes of Q, we have the optimal constant and the complete characterization of maximums. Okay. So the maximizers here, they're also Gaussians, but you see that the lines now, we don't need any square root of -1 to parameterize. These are just the lines 1, 1 and 1 minus 1. They exist in any effect. Okay. And the complete set of maximizers for this extension on the saddle is given by these functions. All right. There's still cones, right? So what do we know about cones? In cone, for cone, so if we take the three-dimensional cone in F4, there's an L2 to L4 extension inequality, which can be put in sharp form in this way with a more complicated constant. There's a degree 5 polynomial numerator. This is sharp. Equality holds for constant functions, more generally for functions of constant modulus, but this result only holds true when Q is convoluted to -1 by Q. Okay? There are some complications that we cannot overcome in the other case. All right, and one last comment about cones. So remember that when we define cones, here are they. I said, for technical reasons, we remove the origin. This is actually what Lockenhaupt and Tau said. Maybe their first results on the code, they said, for technical reasons, we remove the origin, but that's really not important. If you want to add the origin, nothing changes. Well, that's not the case for sharp results. So if we add the origin to the cone, to the three-dimensional cone, so I call it gamma 30, that's just the cone we have with the origin added. Or even more generally, if we consider the cone gamma 03, which is a bit different. These two cones are the same in half the cases because we map one to the other by a change of variables, but in general, they're not the same. If both of them contain the origin, then our last result shows that constants are not even critical points for the L2, L4 extension inequality on these full cones. Okay, so cones with the origin are radically different from cones without the origin because constants have a chance to maximize one, but not the other. Okay, and this is a new phenomenon. It's very different from what happens in the Euclidean. Okay. Any questions about these results? No?
Okay.
Yes, please.
Why do you assume that Q is congruent to -1.4?
Right, so that is similar to the previous assumption. This has to do with -1 being or not being a square, at which point you have special lines that tell us more about the geometry of the cone in one case, but not in the other. So we can solve the problem in one case, but not in the other. I'm not saying that when Q is not over to -1.4, constants are not maximizers. I just don't know how to do it. Okay. All right, so how much time do we have?
Until
Now I got this. Until 50. Okay, we have plenty of time. So I suggest that we try to prove one of these theorems, and maybe we'll start with theorem one. Okay? Theorem one comes with a companion, theorem two, but I'll start with theorem one. But before we go straight into theorem one, let me just tell you about some, let's say, preliminary observations that are useful for pretty much all the theorems. Okay? So this was section 2, section 3 and 4 were slides, we jump to section 5, we are in this for the left. Okay, so the first observation is that this sharp algebraic extension inequalities. By algebraic extension, I mean extension inequalities where the involved exponents are all even integers. This is equivalent to a counting. Okay. So already in the equivalent setting, we use Poincaré to reduce even norms of an extension to L2 norms, the multilinear convolution. So here, these convolutions are even easier, they're just a combinatorial counting. What do I mean by this? I mean that if we take the 2L2K extension inequality, so it comes with a constant, L2 to L2A. Sigma, that's a normalized count. So this inequality is equivalent to a counting inequality. With this looking. Double sums. Over the whole vector space. And for each C in the vector space, we're looking for k tuples, C1 to CA, that add up to C, and all the CIs belong to the surface C. Okay. This is about the functions. And this should be bounded by a certain constant. I'm going to call it the bounding constant. So since there are from L2 to L2, and then we sum FC squared and this to the okay. So these two inequalities are equivalent in the sense that they have the same set of maximizers, same set of maximizers, and the constants are related. So C star is almost the same as R star. You just have to multiply by C K and divide by K to the N. Okay. So in order to understand this inequality in chart form, it's enough to understand this inequality in chart form. And from here to here, and you remove the hat, so oscillation is gone, and you just have a simpler counting code, which I hope I will show is still an interesting one. Okay. And the proof of this equivalence is that there's not much to it. We just open this and we use a bunch of definitions, we use the definition of the extension operator, we use the orthogonality of the characters, and the numbers is 3. Okay. All right, so all these sharp extension inequalities, we actually work with them in this calculation. Now I guess I need some space, so bit of break to erase reports. So, the first prelim was this equivalence between algebraic extension and a counting problem. The second board will be about some elementary facts of number theory over finite fields. Number over finite fields. And this is probably a recap, but I just need three ingredients to make the subsequent construct. So the first one is the Legendre symbol. So the Legendre symbol is just a useful way to capture information about whether A is or is not a square modulo P. Okay, so P is a prime number. If we call Q is P to the n. P is an odd prime number for an integer. So Legendre AP takes three values. It's either 1, -1, or 0. It's 1 if A is a square, but not 0. I mean, 0 is always a square, but for 0 we reserve 0. So if A is a square in FB, -1 if A is not a square, and 0 if A is. Okay. So the Legendre symbol is a completely multiplicative function of its top argument, and turns out to be useful for a number of things. For instance, to compute Gaussian sums. Right? So Gauss sums have the second ingredient we need. So Gauss sums are usually parameterized by A, which is just a non-zero element field. Sometimes I even FP cross as the field in the origin. So if you have such an element, the Gauss sum associated with A, that's just E to the A x squared. X ranges over all elements of P, and it turns out that these things can be evaluated. Okay? So if you want to think about this as a discrete analog, this oscillatory interval with a quadratic phase, to which you could apply, for instance, under quadrant for K greater than 1 and get a sort of a square root cancellation. So there's square root cancellation here. So this guy, first of all, the first observation about the value of this Gaussian sum can be computed just by the knowledge of the Gaussian sum A plus 1. And of course, there's a sign here. This can be plus or minus 1, and that sign is given precisely by the Legendre symbol A and B. And what's S1? So S1 is just the Gaussian sum E to the x squared, where x ranges over elements of your field, FB. And as I said, there's square root cancellation, so the absolute value of this sum will be square root of P. But in general, this is a complex number, which might have phase, the unimodular factor associated to that. And that's actually a non-trivial problem. So Gauss himself, from what I read, was very quick to realize that there's square root cancellation. The absolute value of this complex number is square root of P, but determining the sign is a problem that took him a few years. 4 years in one reference, 7 years in another reference. I'm not sure exactly what happened. But eventually he did compute it. And so this x on P turns out to be either 1 or I. And this is depending on the congruence class of P mod 4. Okay. So if P is congruent to 1 mod 4, x on P is 1. Otherwise, if P is congruent to 3 or minus 1 mod 4, x on P is I. Okay. And this is not, I mean, the knowledge of this sign will be important for us. And it's also important for a number of applications. For instance, quadratic reciprocity. Which is one of the things that you can do with Gauss sums. But for that, you need to have knowledge not just of the size of the Gauss sum, but also of the sign of the epsilon p. Okay, so quadratic reciprocity is tells you that these two problems, namely the problem of determining whether P is or is not the square mod R, and the problem of determining whether R is or is not the square mod P, a priori those are completely independent problems. It turns out they're not. Okay, they're related in the sense that the product of these two numbers. Remember, both of these are basically 1 or -1. There's a few degenerate cases in which they're 0, but this is a product 1 and -1 in most cases. And so this is power -1, and that power is P minus 1, R minus 1 over 4. What does this mean? This means that this product is 1, except if both P and R are both congruent to 3 mod 4. Okay. So in all other cases, these two values are the same. P is a square mod R if and only if R is a square mod P. The only exception is when both P and R are congruent to 3 mod 4. In which case, one is the square, if and only if the other one is not the square. Okay. Usually, quadratic reciprocity, you open just an elementary number theory book, and quadratic reciprocity is usually formulated for primes, for odd primes with some complementary formulas for -1 and 2 and so forth, but it also holds for general odd co-prime integers. And the proof is just by induction, and we need that a slightly more complete version. Okay, so here P and R odd co-prime integers. Okay, so that's what we need from number theory. We already counted. But one last ingredient before we dive into the proof is these slightly more exotic aspects of the geometry of finite fields that enter the world. That has to do with the number of points in conics. Okay, so let's consider conics. The conics in the plane. So I'm basically talking about ellipses and hyperbolas, and how many points lie in ellipses and hyperbolas in the two-dimensional vector space over F. Okay, so these conics can be parameterized by two parameters, C and R. So this is the set of points x1 in F cubed squared, such that x squared minus cy squared equals 1. Okay. So for different values of C and R, you have different conics. Turns out, of course, conics are all finite number of points, right? Everything is taking place in F squared. Turns out that these conics come in 5 different sizes. You can think of them as small, medium, large, extra small, extra large. They come in 5 different sizes. Pretty much all of them are going to be important for us, except the most basic one, which is the fully degenerate case, which is when both C and R are 0. If both C and R are 0, this is just a set of points for which x squared is 0. X squared is 0 forces x to be 0, and you have complete freedom in 1. So you have cubes. Right? Fully non-degenerate, not very interesting, but everything else is interesting. So Q of C is 0. If C is not a square in F cube, this is just 1 point. It's easy to see why. C is not a square. So R is 0, that means x squared equals cy squared. C is not a square, so you cannot solve this unless both x and y are 0. That's the one. This is equal to extra. So this was medium size, this is extra small. It's just 1. Okay, well, what about the remaining case when R is 0? If R is 0 and C is a square, but not zero, so a non-zero square, then there are lots of points. There's actually 2q minus 1 points. If C different from 0 is a square. And this is also easy to see. Why is that? So R is 0, so we're solving x squared equals cy squared, but c1 is a square, so we can call it omega squared. So x squared equals omega y quantity squared, which means that there are actually 2 lines that could go through a common point. Each of those lines has q points, so you will have 2q points, but there's a common point. So it's 2q minus 1. Okay. This is the biggest size. Okay, we have 3 out of 5. Now the remaining cases correspond to non-zero R, depending on whether or not C is a square modulo. Okay, so QCR turns out to be Q minus 1 if C is a square, and R is non-zero. R equals 0 case we've already covered. Okay, so this is small size. And that's also not hard to see. What's happening? So if C is a square, then you can call it alpha squared. Okay. Which means that you can change variables. So you can change the variables from x y to x minus alpha y, x plus alpha y. And that means that this equation, x squared minus alpha squared y squared equals r, you can write it as u v equals r. This is u, and this is v. But r is not 0, so neither u nor v can be 0, which means for a given u, v is v minus 1r. So for every non-zero element u, you have a well-defined choice. How many non-zero elements are there in Q? Okay. All right, in the remaining case, I guess it's the large case. That's Q plus 1 if C is not a square and R is different. If C is not a square, Q and R is missing. Okay. So notice that the small, medium, and large are all very similar. Q minus 1, Q, and Q plus 1. The extra small is really small, and extra large is really large. The proof here is a bit more complicated. It uses a tiny bit of Galois theory, and maybe I'll skip it for now. That to start thinking about this is to notice, okay, C is not a square, so you cannot do this change of variables. You can do that change of variables because alpha doesn't exist. There's no alpha such that alpha squared equals C. What you can do is consider a field extension and consider an element alpha in the algebraic closure for which alpha squared is C, and then consider the field extension F Q joint alpha, which is lambda between 2 over FQ. And then use a bit of what's known about Frobenius automorphisms and so forth. So this comes through, but it's a bit long, and for the sake of time, I'll skip it. Okay, but that's the fifth size of these projects. Okay, 1 to Q minus 1, Q minus 1, Q plus 1 will be the relevant values. Any questions? These were the preliminaries that I needed. We can start with the proof. If everyone's happy. Yeah. All right, so preliminaries, counting, Gauss sums of the direct reciprocity, and the size of conics. So, let's see. Let's please here. Here one is still up there, so I don't have to. Okay, so remember, this is the finite field analog of Folsky's first result, right? L2, L4 on the problem. What did we do then? The first thing we did was computed actually by two different methods, the twofold convolution projection measure on the problem. We first did some delta computations, and then we used invariances of the Schrodinger equation. We noticed Galilean transformation plus a parabolic rescaling showed that any 2 points have the same value on the interior of the system. So here we'll take the first one. Let's compute. I think I call it sigma. Again, sigma is normalized quantum measure. Let's compute sigma from volume sigma by Fourier inversion on F. Okay, so if it's Fourier inversion, we're going to invert the square of sigma hat. Turns out that sigma hat, this is well known, is the sum of the Dirac delta at the origin plus what's called the Bochner external, okay? Which, so this is which is defined in the following way. So it depends on two variables, x and t. X is a vector, t is a scalar. And if t is 0, this is 0. If t is not 0, this is 1 over the size of p squared, the number of points in the parabol, times sum e to the x dot c, the vectors, plus c squared. And here, sum is over points in the parabol. So you have c squared in P2. And this can be computed. Okay, this was already computed, explicitly computed in the paper of Mock and Hoffman. I raised it from the board, but that paper has this explicit computation. And you can imagine, right? This kind of looks like a Gaussian sum. So you're going to complete the square, there's a translation, there's an additional parameter, and what you get at the end of the day is p to the minus 2 ST squared, ST here denotes the Gaussian sum, the SA, is ST, and modulate. So times E and minus x squared. Okay, so recall here what we know about Gaussian sums is that ST is T, Lagrange TP S1, and S1 was the square root of P times epsilon P, which could be 1 or minus, 1 or I, depending on the congruence classification modifier. And okay, so let's go for inversion. We want to compute the twofold convolution of sigma at a point c tau. By Fourier inversion, this is sigma hat, for which we have an explicit expression, squared hat at the point c tau. Okay. This is Fourier inversion, it holds. I didn't show you how it holds, but we have all the ingredients to check that it holds, in particular this orthogonality statement for E. Okay, and now we have an expression for that. So we just squared, we get p to the minus 4, s to the 4, exponential of x squared over 2t. That's what happens when we take the square. And we just take the inverse Fourier transform. So the result is 1 plus p to the 4th. Sorry, this one is here because I was hesitating. This has to be 1. Let's see. So there's it's corresponding to the delta. P to the minus 4, S equal to 4, and then exponential of minus x squared over 2p. This is a sum over x and t in f squared plus f cross. So t is not 0 because if t is 0, we already have this contribution here. Okay, this is what you get from squaring sigma hat, and then you have to take the Fourier transform. So e to the minus x of c, e to the minus t. Okay, That's an expression for the twofold convolution. Now we want to say something about it. And similarly to the way to compute this, which I didn't visit in detail, now I can visit details. And so you can notice that this product of two exponentials is just e to the minus 1 over 2t x plus t c squared times e to the t c squared over 2. Okay, so I'm performing a similar trick. This is like completing the square, and to complete the square, you have to pay a price. There's an extra term that's not there, so you put it. Why is this useful? This is useful because this is a sum in x and t. You can choose the order, but it's a finite sum. The b is not the order. So if you sum in x first, the only thing depending on x appears here. And so you can do a shift with the x variable and get rid of this extra t c term. At which point you'll just have options. That's the usefulness of this completing the square and doing a shift in the x variable. Okay. So you do that, and when the dust settles, this equals 1 plus epsilon p squared over p. You get rid of the sum in x that just produces a power of the Gaussian sum. So you just have a sum in t. The sum in t is over all t, all non-zero t in fp. And what contributions do you have? Two of them, right? You have e to the t c squared over 2 and e to the minus theta. So t is a common factor, and your square is c squared over 2 minus theta. Okay. Does this ring the bell? If you remember the computation we did for the parabola, what do we conclude then? We conclude, oh, that convolution is constant in its support. What's the support? The support is just an enlarged parabola. It's exactly what's happening here. Tau equals c squared over 2 is this enlarged parabola. Now it doesn't make sense to talk about the interior of the support because that would mean that tau is greater than c squared over 2 in finite fields like this financial. Right? But the boundary of the support is here. And this sum has two different values depending on whether or not tau equals c squared over 2 or doesn't. So end result, okay, after all the dust settles, remember that epsilon p squared. Epsilon p was 1 or I, so the square is either 1 or minus 1. These are all real numbers as they should to the counting volumes. And so this is 1 over p times two possibilities, either p plus minus p minus x1, if you're on the boundary of the convolution, or p minus plus 1 otherwise. What will these sign choices mean? So the first choice of signs, plus minus, that will be 2p minus 1 and p minus 1, corresponds to p congruent to 1 of them. The second choice of signs, that means 1 upstairs and p plus 1 downstairs, corresponds to p congruent to 3 1. Because the only difference between the two is this x on p squared. This is 1 or minus 1, depending on the congruent space of p. Okay. I'm just going to write it as like first choice of signs corresponds to p congruent to 1 minus 1, and second choice of signs corresponds to p congruent to minus 1. Okay, so that's it. We computed the twofold convolution, and we saw that it takes a few values. What are those values? Well, modulo the p normalization. We have p minus 1 or 1, p minus 1 or p plus 1. Where have we seen these values before? They're precisely the four sizes of coordinates that correspond to the non-completely degenerate situation. Okay. 1 to q minus 1, q minus 1, and q plus 1. So, not surprisingly, there's an alternative proof for this convolution computation that doesn't go through Fourier inversion, it just goes through counting. Okay, we can just count the number of solutions. That alternative proof has an advantage and a disadvantage. The advantage is that it works for general Q, not just P. Notice that these computations were on FP, and we're interested in more general FQ fields. Okay, with a counting proof, you get Disadvantage is that this proof generalizes very nicely to higher dimensions and arbitrary degrees of nonlinearity, whereas the counting problem becomes very hard. Okay, so let me show you. Of course, the formula is a bit complicated, but that's what we get. Right? This is what we get using Fourier methods for general dimensions and general degrees of nonlinearity. Okay, so here D, the dimension, and K, the number of convolutions, is arbitrary. For technical reasons, we need a prime to be strictly larger than K, odd prime again. And this is an expression, an explicit computation of the K-fold convolution of a normalized surface measure on the problem. Okay, for any K and any D. The disadvantage is that this only works on FP, not on FQ. For FQ, we would need to solve the counting problem, and that sounds a bit intractable at the moment. The expression is nice. I mean, there's powers of this epsilon p that we define up there, 1 or I. These all turn out to be real numbers, of course, as they happen. There's a function phi, which is given by these 3 different expressions, depending on the parity of the dimension and of K. What's interesting is that in the first 2 cases, that's even dimensions and odd dimensions and degrees of nonlinearity, the convolution only takes 2 values, like here. Here, there's 2 values on the boundary and outside the boundary. These values precisely correspond to being on the boundary, tau equals c squared over k, because this is a k-fold convolution, or not. The third case, when d is odd and k is even, takes on 3 values, because there's an extra term, which is formulated in terms of a Legendre symbol. And so depending on whether c squared over k minus tau is or is not a square one p have 2 different values, but then there's the third situation in which c squared over k minus tau is a multiple of p. Okay, so these 3 values are an additional contributions. I have 20 minutes, right? Yeah. Okay. So now that we know the convolutions well, let's see how to put all of this together and prove theorem 1. I think I have the words, so second break. Please don't forget the preliminaries because we will need it. So we want to put theorem 1. So let's go back to theorem 1. Click this. Okay, so we already computed the pointwise values of the left-hand side in the very special case when f is 1, right? So sigma convolved with sigma, we know what it is. To analyze general functions, we do what we did on Tuesday for sharp Strickhart's on for the Schrödinger equation. We take 2 points, c and tau, and we ask ourselves, how can we write these 2 points as a sum of 2 points on the problem? There should be c1 plus c2, such that tau is c1 squared plus c2 squared. Remember that we have these 2 deltas, right? And the first step was to reduce the two deltas to just one delta by using one equal, replacing it in the second one. Right, so we do that. From here, it follows that tau is C1 squared plus C2 squared, but C2 is C minus C1. So it's C minus C1. I'm making an effort to put all the vector symbols, I'll probably forget. Okay, this can be equivalently rewritten as C1 belong to some circle of center C over 2 and radius 2 tau minus C squared over 4. Okay, so here my circle, I'm defining the circle of radius gamma. The circle of the center of the gamma and radius r as the set of all points in FQB such that gamma minus x squared equals. So actually, it's not really the radius, it's square root of the radius, but we don't feel we don't want to. Okay, so you can check that this equation is equivalent to C1 belonging circle of this kind of radius C over 2, of center C over 2, and radius 2 tau minus C squared. Of course, the radius vanishes precisely at the boundary. Right? This radius is 0, precisely 1 tau is C squared over 2, which we've seen is a special value for the convolution corresponds to the boundary. All right. So, inequality 2 from here on by the counting procedure that I described can be equivalently written in the following. So this is a double sum over all points C tau in FQ3 of XC1 of C minus C1 squared. And here C1 belongs to this circle that we completed. It's the circle of center C over 2 and radius 2 tau minus C squared over 4. Okay. And what we want to check? We want to check that this is bounded by not exactly that constant, but remember that there was a price you paid when you went from the restriction constants to the counting constants. Had to do with the size of the parabola and the measure of the number of points on the field. So we have to multiply that constant by q, and we get q plus 1 minus 1 over q times the ultimate length. Okay, this is what we have to check. And maybe one thing to observe is, in the case of the Euclidean parabola, the proof was very simple. We just used the fact that the convolution was constant inside, so there was a trivial holder that extracted the value of that constant, the value of that convolution, and Cauchy-Schwarz and holder were equalities at the same time for Gaussians. So what happens if we do exactly the same thing here? So one sort of trivial bound would be to bound this by the sum of the sizes of circles times the ultimate length for square. Right? This is a trivial bound. I can just say I take the largest circle and I use Cauchy-Schwarz for each theta in FQ. And this is exactly what Fossel does. It works in the case. Here it doesn't. Why does it not work? It doesn't work because this soup, we completely know. We have the size of conics. We know what the maximum size of a circle is. It's either 2q minus 1, that was the extra large situation, which happens when q is smaller than 1 by 4, or q plus 1, which I guess is the large situation, where q is smaller than minus 1. And both of these numbers are strictly larger than the optimal constant that I claim to be the case. Of course, here you come close. This is q plus 1, and this is q plus 1 minus 1 over q. But you still have to find a way to make this minus 1 over q. So what's the difference? What's the reason for the Euclidean technique not to apply to it? Well, in the Euclidean case, we were always saying something about the convolution being constant in the inside of the support, and we didn't care about the boundary of the support because it had zero measure. when we integrated over R1 plus 2, 1 plus 3, it didn't matter. Not the case here, right? Every point counts. This is counting measure. So there's a small boundary, but the boundary contributes. And actually, it's quantifying this well. The q plus 1 comes from the non-boundary terms, and then minus 1 over q, which we still have to somehow reduce, comes from the boundary terms. Okay. Yeah, so I'm not going to write it, but the issue here is that the boundary of the support of the convolution has positive measure. Right. Okay, so how to finish? There are two cases. There's the easy case and the not so easy case. So this is the easy case. Easy. Inverted columns. It's not so easy. And higher inverted column, but it's not so high once you know this. Okay, so let's start with the easy case. Easy. 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 That's q over to minus 1. Why is this easy? This is easy because this is the case in which minus 1 is not a square in FQ, and therefore circles of radius 0, as you would expect from your Euclidean intuition, have just one point. Okay? It's easy because minus 1 is not a square in FQ, and because of that, circles of arbitrary centers of radius 0, they are singletons. Okay, so in this case, we're going to split the analysis of the left-hand side into two sets. There's the critical set, where tau equals c squared over 2, that's the boundary element support of the convolution, and everything else. Everything else means the complement of the critical set. Cauchy-Schwarz like this is enough. We have to be a bit more critical and more careful about the critical set. Okay? Split between critical set C2. That's just come in. It's the same C down of Q squared, such that is C squared over 2. And its complement of Q3 take away C2. And here, Cauchy-Schwarz surfaces. What does it mean? Cauchy-Schwarz surfaces. Okay, so now I need to write one big equation. I'm sorry for that, but I need to finish. So I'm going to repeat the left-hand side. C1 is in the circle, the radius is 0 and 2, so the center is 0 and 2, and radius is 2, and it's C squared over 2. I'm just copying what we have upstairs. All right, now I claim that this is bounded by, so I'm splitting this guy into two regions, critical circles and the complement. On the complement, I'm using Cauchy-Schwarz. I'm using Cauchy-Schwarz and I'm picking up a factor of q plus 1. This was the large contribution from the convolution. Okay, so after Cauchy-Schwarz, the square comes in inside the second sum, and I just have FC1 and C minus C1 squared. And the sum should be over C tau in the complement of the critical set, but I'm actually going to add the contribution of the critical set, and then I'm going to subtract it later on. This is, if you want, it's transparent. You're adding something and then subtracting the exact same thing. Okay, so this is C1 in the circle, let's say the 0 2, radius 2, now minus C squared over 2. Okay. I already used Cauchy-Schwarz in the complement of the critical set. Now, I'm left with the critical set contribution, so that means C and tau minus C2. I haven't touched what happens haven't touched what happens inside the critical set. So the absolute value is still outside the sum. C1 S. C2 over to 0. Remember that the radius is 0 precisely when you're in the critical set. And what do I have to do? I have to subtract the contribution from the critical set that I added here. So I'm going to subtract exactly Q plus 1 times this guy, but for C and tau over the critical set. C1 is again the circle of center C over 2 and radius. Okay. So, sorry, this is a long equation, but not much is going on here. I'm just using Cauchy-Schwarz on the complement of critical set. And I'm adding and subtracting the singular contribution for the critical circles. Of course, if there was another way here, of course, okay. Is everyone happy with this? All right. So it turns out that this quantity, the second line, which again is the contribution of the critical surface, the boundary of the convolution. This is the quantity that we need to balance. And the analysis of this star quantity turns out to be much simpler in the easy case than in the hard case. Why? Because the easy case is easy because circles of radius still just have one point. So all these sums that look very complicated, they're sums over circles of radius 0. There's just one contribution, which is the center of the circle. So every time you see C1 in these expressions, you can assume that C1 equals C over 2. And so the sums just boil down to one element. Here, for instance, we will have f of C over 2. F of C over 2 quantity squared. So that's an f of C over 2 quantity for the power. And the same thing here. So let's see what happens in the easy case. So easy case implies that the circle of radius C over 2 and radius 0, center C over 2 radius 0 is just an angle 0. So star, this yellow star, is very simple. This is just the sum of f to the 4th, which appears 1 minus q minus 1 times. So minus q times. Right? You will have contribution f of C over 2. But for every C in the critical surface, you have exactly 1 point above. So you're capturing every point of the problem exactly the same. And how many do you have? You have one contribution here, and you have 2 plus 1 contributions there, and you're minus. It's 1 minus 2 minus 1. That's minus 2. Is this what we wanted? Not yet, because we're trying to bound this whole thing in terms of an L2 norm. But to get from here to L2, and just use the line. So by folder or Cauchy-Schwarz, it's bound by minus 1 over here times the same boundary. Okay. This is just one last application for Cauchy-Schwarz. And notice this minus 1 over q was what was missing when we did that very rough estimate, bounding it by the maximum number of points in any circle. And we had a q plus 1 in the easy case. Now we have q plus 1 minus 1 over q. That's the optimal cost. And you can check that all inequalities in this reasoning become equalities for the constant function. And so we're done. We're done for the easy case. What about the hard case? So the hard case is harder because it's not true anymore, right? Now, circles of radius 0, they actually have lots of points. They have 2q minus 1 points. They are unions of lines with a common intersection. And so that case is more complicated. I don't have time to show you the details, but I can tell you that this analysis is still about analyzing the starter, breaking it up into different pieces, and using 5 further applications of Cauchy-Schwarz, very carefully selected, to control each of those pieces. Okay. Then there's the geometric observation at the end. So hard case is 5 further Cauchy-Schwarz plus a geometric observation, which is a whole. So circles now. Let's say we have circle, radius 0, center, over 2. This is the union of 2 lines. We can call it L plus and L minus. They intersect at the point C over 2. And the geometric observation is that if you sum the indicator function of C1 belonging to L plus C, and C2 belonging to L minus C, and you sum this over all C and L into the surface, this equals 1. So, in other words, for arbitrary C1 and C2, there's precisely one guy in the surface for which the corresponding system of lines will pass through each of them once precisely. Okay. Now, the hard case has a longer proof. You are invoking more inequality, so you can extract new information. Every time there's a Cauchy-Schwarz, and there's going to be 6 or 7 of them, you can extract information. And that turns out to be enough information that in a hard case, we can actually characterize maximizers. Okay, theorem 2 is about the hard case. The hard case for the sharp inequality turns out to be the easy case for the characterization of maximizers, just because the proof is longer. And every time we have an inequality, we extract information about the cases of equality. We combine all of that, and we have theorem 2. Okay. So maybe this is a good time to stop. Yeah. Thanks.
Are there any questions?
I forgot statements of this theorem, but did you at all consider the case that characteristic is given that equal to 2?
No. So you mean P equals 2, right?
Yeah.
So Mockenhaupt paper starts with the following line: let P be an odd prime, and then they develop the restriction theory. So I've thought about that, but I think that this kind of surfaces, paraboloids, the columns, and so forth, they're given by degree 2 equations, and x squared equals x in characteristic 2. So I think whatever curvature means in finite field center, I don't think it's well understood, but whatever it means, it's not present if x squared is equals by x. So I haven't seen anything with the restriction theory in fields of characteristic 2. I will be interested if anyone knows, but I don't.
Another one? Yes. First, maybe you are familiar with but like for if you, I mean, you did the problem with the tone, saddle, what about the speed?
Great, thanks. This was the question I was hoping for because I forgot to tell you about the problems for the data. Right? So the problems I suggest are, first of all, non-endpoint parabolic extension. You've seen that I computed the two-fold convolution of parabolas on the board, then I gave you the general formula for the k-fold convolution general dimensions. It should be possible to take that formula and come up with a sharp version of the corresponding. Maybe it's not so interesting because it's not endpoint, but that's the green problem. The yellow problem is precisely what you're describing. So sharp, I haven't talked about spherical extension in finite fields. There are results, even though Mockenhaupt and Tal didn't consider, they said, for serious situations it's more complicated, so they did it for future study. And people have studied Josevich and Gold. It turns out that these expressions for sigma hat for the sphere, they don't involve Gaussian sums, they involve Clusterman sums. And as far as I can tell, there are no explicit expressions, closed form expressions for the value of constraint sums. And even if there were, so we still have a counting argument, right? And the counting argument seems to reveal that these convolutions, spherical convolutions, they take on many different values, not just 2 values or 3 values. Okay. So even if we could compute the convolution of spherical measure exactly, which I still can, turning that into a sharp inequality is not true. And by the way, really interesting problem I think would be to take these results and somehow capture, recover non-Euclidean results or get new Euclidean results. That's my suggested comment.
So that I do, if I can ask, I don't know, in the spirit of this, like, what about
That's another very good question. Absolutely.
So,
That could be a transition, right, from finite fields to realities, from realities to Euclidean. I don't know.
in these counting properties,
I think they're different. Now we don't have just a finite number of columns anymore. There's our measure.
Any other questions? Interesting.
So in these theorems,
Say that again.
in these theorems that you showed, when number of elements of the field goes to infinity, then constant goes to 1.
Right.
And is this constant 1 the same Euclidean case or different?
Depends on the normalization for the Fourier transform. You can set up things so that you also get constant 1 there. For instance, there's a nice reformulation of sharp Strickers for the Schrodinger equation in terms of a hypercontractive inequality in the spirit of Beckner. So Beckner was the first thing I talked about, right? Sharp Hausdorffian. So some people have tried to emulate Beckner's proof in the context of sharp restriction for the parabola in the hope of getting the non-even exponents, sharp inequalities and non-even exponents. And so at least the step 1 in Beckner's proof, that's a hypercontractive reformulation of Strickers, that works. So you can get it with constant value.
And what kind of application of this kind of problem in finite fields or
What kind of, sorry?
applications or more generally, what motivates this kind of problem in finite fields? I do not know finite fields. So
I mean, I tried to motivate in the first bullet, but it's not here anymore, by saying that finite fields are somewhat similar to RD. If you have difficult problems in Euclidean space that you can solve, that you cannot solve, maybe if you solve them in finite fields first, that will give you some hints on how to attack the Euclidean problems.
you can extend this from finite fields to RD?
Not the results, maybe techniques, ideas. I mean, a good example is Beer, right? Beer proved finite field KK by using the polynomial method, and polynomial method on steroids has been crucial for the recent progress in restriction, Euclidean restriction. So not the results, but the methods.
And methods are simpler.
Extending the results would be great, but I don't.
The methods are simpler, like because here it is finite and
I would say they are inspired.
Let's give one thanks for Diogo to the full series of lectures.